First, thanks for inviting me here. It's great to be here today. So 70 years ago, a woman called Gertrude Blank, who had just graduated with a PhD from Cornell, in fact, was running the Mathematical Tables project, which had about 300 clerk workers, and their task was to tabulate all the special functions and the Gauss quadrature rules of the time that was deemed useful. Because you see, back then, if you wanted to integrate or you wanted to evaluate a Bessel function, you'd go to one of their 28 volumes that they published, and you'd look at the right table and you'd carefully extract out by hand the digits that they had computed for you. Of course, nowadays we have extremely fast digital electronic computers at our disposal. So if we want to go and evaluate a Bessel function, as of now, we just go to a piece of software and we get that number on the fly and extremely cheaply. This has completely changed the way numerical analysis fits in computational science. Now we care about not only getting the right answer, but getting the answer fast. Numerical analysis is a field where we carefully use very well-chosen numerical approximations to derive fast and numerically stable algorithms. We're sort of at the interface between applied and classical analysis. Not only do we want to give people industrial strength software that they can really use, but we also want to prove some theorems to give it sort of a rubber stamp of approval. This echoes in my work, my past research. For instance, working with some people from Manchester University, we were trying to look back at classical algebraic geometry and their work on resultant methods, and trying to use that to derive a numerically stable root finder for polynomial systems. And eventually we produced a piece of software which can now find the global minimum or maximum, for instance, of a very high degree bivariate polynomial. Here I've taken the fourth cyan digit challenge, which has 2,720 local extrema, and the task here is to find the global minimum, and that's the red dot. Or, for instance, taking classical approximation theory and using that to understand how low-rank approximations of functions converge to bivariate functions. And then eventually producing the 2D analog of the Chebfun project, which is for computing with functions in two variables. So here I've approximated a function and it happens to be of rank 65. In fact, the cyan digit challenge at the time was considered extremely hard, but actually the function that was chosen was actually of rank 4. So it's kind of the rank, simplifying things with low rank approximations happens to be very useful.
What's the rank of the function?
The rank of the function is the number of terms that you need. The numerical or the mathematical rank is the number of terms that you need of this form here to nail that function exactly. So, for instance, a function x times y is of rank 1 because it can be written as a product of x times y.
So most functions have infinite rank.
Most functions have infinite rank, but numerically, if the function is analytic or is differentiable or k times differentiable, it will have a very precise decay rate, which you can then chop off when things get below machine precision. So mathematically, it will have an infinite rank, but numerically, it will have a finite rank. For instance, cos of x times y is of numerical rank 6, but mathematical rank infinity. Does that make sense? So if you know the Chebfun project is about replacing functions by Chebyshev expansions. This is the definition of a Chebyshev polynomial. It's a cosine that has been with a change of variables. And this is a Chebyshev expansion. If you know anything about Chebfun, you will know that it's about replacing functions by Chebyshev expansions, which are like the non-periodic analog of the Fourier expansions. And that was exactly true, that statement, 3 or 4 years ago. But nowadays, things are very different, and it's sort of a secret that we don't tell people, because if we tell them, they get a bit nervous. And that is if for instance, if for instance, I want to go and solve a high-frequency Helmholtz equation in Chebfun. It's taking some time the first time. Okay, let me do that again. It's just loading. For instance, if you wanted to calculate the high-frequency Helmholtz equation in Chebfun, this is using a spectral method. So classically, classical spectral method will not work on this problem because it's too high frequency. But underneath the hood in this high-frequency Helmholtz solver, we're not using Chebyshev polynomials at all. We're using polynomials called ultraspherical polynomials. Or, for instance, if you were calculating 1,000 Gauss Legendre nodes and weights, I just computed them in 0.03 seconds. Or if I want to compute 100,000 or maybe 1,000,000 Gauss quadrature nodes and weights. These are classically considered extremely hard to compute. Here I've just computed 1,000,000 in a fraction of a second. Obviously, underneath the hood, I'm not using Chebyshev polynomials here. I'm using Legendre polynomials. And I'll explain exactly how this works. Or for instance, if I wanted to compute the 100-degree best L2 approximation to a crazy oscillatory function, which is in the blue, you can hardly see it. And then the red is the best L2 approximation of degree 1000. The reason that this was such a fast computation, because classically it's a slow computation to do, is because underneath the hood we're carefully using asymptotic approximations of Legendre polynomials. We're very careful. Or if we wanted to compute the convolution of two functions, so here I've convoluted two functions together. This is classically a very hard computation, but underneath the hood we're using Legendre polynomials and Bessel functions, not Chebyshev expansions. So the secret that we do not tell anybody is that underneath what appears to be all about Chebyshev expansions is actually about many other different special functions. And this talk I'm going to explain how we need fast algorithms for those special functions too. Not just the Chebyshev basis, we need them for the Jacobi basis, the ultraspherical basis, the Bessel basis.
What does this picture represent?
The blue function here is crazy oscillatory and not very smooth function. And I've used this Gaussian here to convolute it with this Gaussian to smooth it, to mollify it.
Is the function x sine 1 over x?
No, the function is
No, but which color is the function and which color is the convolution?
the function is blue and the convolution is in red. The smoother is in red.
I do here sine 1 over x.
Yeah, there's sine 1 over x times sine 1 over sine 1 over x on AB. Okay, so it's some crazy function that is really complicated on a very particular point, and I've just convoluted it with a Gaussian to make it smoother.
And let's see what those two things
So they change color now. So the green is the crazy oscillatory function, and the red is the smoothed out version of that after I've convoluted it. I've mollified it. But the reason this computation was fast is because underneath we're secretly using special functions all the time. And we need fast algorithms for those special functions too. So that's the aim of this talk, is to derive fast algorithms for those special functions. So the reason that fast algorithms exist for trigonometric functions, for instance, is because when you look at the graph, they have constant phase and constant amplitude. It has a very algebraic structure that you can use when you go to use a fast algorithm. Or, for instance, the reason why Chebyshev expansions and Chebyshev polynomials have related fast algorithms is because they have a constant amplitude and they are just a change of variables away from a cosine. But this is not true for other special functions. They're not trigonometric on their whole domain. They're not trigonometric like everywhere. For instance, if I take the Legendre polynomials, for instance, they are not trigonometric on their whole domain, but they are, we often observe them to be trigonometric away from their endpoints, and Bessel-like at the endpoints. Or for instance, if I take a Bessel function, often it's said that Bessel functions are just trigonometric-like functions that decay like 1 over square root of z. Or the same can be true for the Airy function, or the Jacobi polynomials. You can pick many special functions, and you'll get this trigonometric-like behavior in some regime of their graph. And to generate fast algorithms, we will have to carefully understand exactly when a function is trigonometric-like and what exactly we mean by that statement. Luckily, it was a hobby of classical analysts 100 years ago to exactly understand this slide. And so, for instance, Stilches in 1890, he wrote down this asymptotic expansion of this Legendre polynomial. And this precisely tells us exactly when this special function is trigonometric-like. For instance, you can see if you just take the first term, you just plug in m equals 0, you'll see that it's like a cosine in the middle where the denominator sine of theta is close to 1. But when sine of theta is very, very small, it blows up. So it's trigonometric-like in the interior, but we don't know what happens outside of that region.
Could you outline why that is an asymptotic formula? What is small? Why do things get small when m and n get small?
No, as n goes to infinity, the error term between the m term, so if you pick m equals 10, say, as n goes to infinity, 10 terms of this asymptotic formula, this formula here, will converge to Pn of cosine of theta as n goes to infinity.
Well, I agree that's what it means to be an asymptotic development, but at the moment I don't see why, when n becomes large, anything becomes small.
But I've hidden these constants in here. This constant.
Oh, it's hidden in that constant.
Yeah, there's constants in there that come small. Yeah. It's the constants that come in that term, that convergent series. Those h of mn converges geometrically with n. So it gets smaller with n as n grows. So there's also Bessel functions. Hermann Hankel wrote down asymptotic formulas for Bessel functions. They happen to look like this. But this tells us exactly, it makes precise that observation, that these are cosine, they look like trigonometric functions, cosines and sines, with that 1 over square root z decay. These are the asymptotic formulas that we will use to derive fast algorithms, because it tells us how to relate it to cosines and trigonometric functions, and that's what we need. But there's a numerical pitfall with these, because when they were designed, they were not designed with, when they were derived, they were not derived with numerics in mind. And this has caused confusion, actually, in numerical analysis for a while. They're very different. They're not convergent series. You've got to treat them very differently. For instance, if I pick z equals 10, and I slowly increase the number of terms that I take in this series, I would expect it to convert. If it was a convergent series, I would expect to have nice uniform convergence. But this is not true for an asymptotic expansion, or it doesn't need to be true. So for instance, here, you can see the error. It goes down to machine precision, bumbles along a bit. But if I take too many terms in the asymptotic expansion, I suddenly lose the accuracy again. Right? So instead of fixing z and increasing m, you've got to flip that picture. You've got to fix m and look and ask for what z does this asymptotic expansion, when is that a good approximation? So for instance, when m equals 10, this graph shows us that the asymptotic expansion is accurate to machine precision for any z greater than 18. So this is the way you have to use them. You have to think of them as fixing m and then asking for what regime does the asymptotic approximation, when is it accurate, for what regime? And we must be careful of that all the time. So I will be very strict on myself and only use an asymptotic formula where the error is at machine precision, so I effectively lose nothing. And I will only use an asymptotic formula if I know exactly what the error term looks like. I have an explicit bound on it. That's tight. That's my rule, so that I'm not somebody that's thinking in this picture, I'm thinking in this picture. So I'm going to give you two applications of these asymptotic formulas and how we're using them in Chepfun to compute things. The first one is computing Gauss quadrature rules. And the second one is fast transforms based on asymptotic expansions, which I'll explain. So computing Gauss quadrature rules. So what you need to know is just one piece of notation. which is I'm going to define the Legendre polynomial, which is some polynomial, as Pn of x. So just remember, Pn of x is the Legendre polynomial of degree n. An n-point quadrature is an approximation of an integral using a weighted sum of n terms with n function valuations, just like this, wk f of xk. Gauss's quadrature is the special choice of choosing xk to be the kth zero of this Legendre polynomial, and wk to be related to the derivative in this fashion. With this exact choice of xk and wk, the quadrature is best possible, in the sense that it integrates polynomials of degree 2n minus 1, which is the highest you can do, with an n-point quadrature exactly. You may know that these are computed by the Golomb-Welsh algorithm, or this is the most famous algorithm to compute these Gauss quadrature nodes and weights. And the trouble is, the Golomb-Welsh algorithm, though it's considered is the most popular algorithm, it is actually a little bit slow, as we found out when we did some experiments. Here's the experiments that we did. The blue line is the one you should concentrate on, the blue lines, and that's the Golomb-Welsh algorithm. That's how you compute the nodes and the weights. And we can see here that the Golomb-Welsh algorithm, out of all the other algorithms I've picked, is the most expensive and has the worst error. But yet it's the algorithm that every single numerical analysis uses to compute these things.
Could you outline what that algorithm is?
The Golomb-Welsh algorithm writes down a tridiagonal matrix related to the three-term recurrence that the Legendre polynomials satisfy. It then works out the eigenvalues and eigenvectors of that matrix.
How does it do that?
The eigenvectors and eigenvalues are worked out by the QR algorithm, typically.
Okay.
And then once you've done that, the eigenvalues of that matrix are the xk, the nodes, and the wk are related to the eigenvectors of that matrix. That's how it works. So the point is, the algorithm that everybody uses seems to be the slowest and have the worst error. But yet there's another way, and the reason everyone uses the Golomb-Welsh algorithm is because they think it's a very beautiful mathematical statement that Gauss quadrature can be related to eigenvalues. But there is another way, and that another way is just Newton. Everyone here knows how to do Newton, and this turns out to be the way to, or one very good way to do it. But there's a catch, otherwise someone else would have done this many, many years ago. And that's, you've got to make it fast, you've got to use asymptotic expansions of these Legendre polynomials. And to make it numerically stable, you've got to do a change of variables. The change of variables is actually really simple. It's this change of variables here. Instead of computing the roots of Pn of x, compute the roots in a different variable by just changing variables into theta. So instead you write x equals cos theta and do a change of variables, and then times it by this function here. You get this from the leading order asymptotics of Pn. This is how you derive this. But you'll see instantly that we turn this quite scary looking polynomial, especially as n gets high, with oscillations that cluster near the endpoints that seem that Newton might struggle on that, to a perfectly nice constant type of phase function. We're going to apply Newton to this function here instead of the other. So what do we need for Newton to work? We need an evaluation scheme for the function. We need an evaluation scheme for the derivative. We need initial guesses.
You also need to tell us what equation you're solving.
I'm trying to find the roots of Pn of x, so I'm going to end up solving, after the change of variables, I'm going to be solving this equation here. I'm going to try to work out the roots of this function. That will tell me the Legendre nodes. It will tell me the roots of Pn of x. Does that make sense?
Yes.
Why aren't they just the projections onto the real axis of the evenly spaced points on the circle?
Because while this picture looks like constant phase, it's only up to 3 or 4 digits. If I wanted those roots to be sheep, this looks nice, but it's not exactly a cosine or a sine. because I've only taken the first leading term of the asymptotic expansion.
It's not Chevy.
It's not Chevy-Chev, yeah. It's
No, it's not
something
Chevy-Chev.
very close, but not quite Chevy-Chev. So we know what we're going to do in the interior when we're away from the endpoints. We're going to evaluate this nice function here now by its asymptotic expansion, and we know that. That was done in the 1890s. We're just going to, every time we want to evaluate that function, we're instead going to evaluate this asymptotic expansion instead. But we need something at the boundaries as well, because that asymptotic formula we know doesn't hold right near the endpoints. And luckily, as we often say actually, Legendre polynomials look like Bessel functions near the endpoints. And there's an asymptotic formula that makes that precise. So we're going to use an asymptotic formula in the interior, where things look like trigonometric, nice, smooth, constant oscillations. And we're going to use this other slightly crazier asymptotic formula near the boundaries. But the point is of using this is now one function evaluation is so cheap. It's almost free. It costs O of m operations. If m is 10, it costs hardly anything.
The h's are tabulated.
The h's have exact formulas. They involve factorials, which you divide out. And they're basically gamma functions. They're nice. Everything's known explicitly. Everything's known explicitly here.
So, Alex, could you say one thing? So you were going to find roots of Pn of x.
Yeah.
Then I would understand how you would look at Pn of cosine, but could you say a little more about how that sine theta to the 1/2 came in?
Yeah. So if I this is perfect. So if I go back to the asymptotic formula of Pn, which is here, and I stick in capital M equals 1. I get a leading order asymptotics for Pn of x, or Pn of cosine of theta. This will tell me that it looks roughly like cosine divided by sine theta to the 1/2. I don't like the 1/2 because then it scales things weird. So if I times this whole expression by sine theta of 1/2, I know that Pn of cos of theta times sine theta to the power of 1/2 is just like a cosine. Okay, that's why I had that
Good,
picture.
okay, thank you. So you say that's just based on that one term?
Yeah.
Because with 2 terms, of course, you'd have more trouble. But
Yeah, if you had 2 terms, you wouldn't be able to do this type of scaling. You can't do
okay,
it.
so it's based on the one term.
Just put
asymptotic.
one term to
That's
take it
amazing.
out. And then you get this nice function, do Newton on this, and your world is easy.
Wow.
Okay, so we're going to use asymptotics in the middle, and asymptotics again at the boundary, but 2 different asymptotic formulas. Because we're always on this change of variables function. And then the theorem, so in the past, everyone was completely scared of doing this way because they couldn't make Newton converge. But here, because everything's nice and equally spaced, like the phase is nice and constant, in fact, basically equally spaced points will converge to the roots. And you can prove this. This is a theorem that if you pick these initial guesses and n has to be larger than some constant, so I've just picked 200, then Newton converges in O of n operations to the nodes, and you get the weights from the formula. So we just have an extremely fast way of computing the Gauss Quadrature weights, and that's how I got 1 million Legendre nodes and weights in a fraction of a second. I just did 1 or 2 Newton iterations on asymptotic formulas, and I'm done. Okay, so that theorem showed us that we could just take equally spaced points, but in practice, we can take better initial guesses, just so that we hardly use a single Newton iteration. So, for instance, if we use really good initial guesses, when n is greater than 5,000, I don't even need a Newton iteration. I have the nodes and the weights for free. They're just there as a formula. They're good up to 16 digits. When n is above 5,000, there's no work to do at all. Nowadays, as of last month actually, there's even better initial guesses. I don't even need Newton when n is greater than 500. So it's kind of, I can just give you the nodes. Evaluate these formulas, and you'll get the nodes and the weights to 16 digits. Of course, if you wanted more digits, you would do Newton on top. Yes.
So your Newton's method for 10,000 took less time than the 1,000. Is that why?
That was probably just the way I was doing it. But there is definitely the crossover point is you don't really get to see that, but you could, in principle, see something like that. Yeah. So I got really excited about this, that somehow the way everybody was computing these things was not actually anywhere close to the state of the art. So I went back and tried to find out why everyone was using Golden Welsh in the first place. So I looked at all these papers, and every time I read a paper, I plotted on the graph a black dot where the year of the publication against the maximum Gauss-Legendre rule that was computed within that paper. And so this is the graph you get. And I've coloured all the red dots with variants of the Golden Welsh algorithm. So these are all, the red dots are essentially the ones that are using the Golden Welsh. The black dots are the ones that are doing many other different methods. And the surprising thing I found was, the Golden Welsh algorithm was never actually the state-of-the-art algorithm. It never was the most accurate or the fastest step. Historically, there's always a black dot above a red dot, and it the way, I think the only reason that Golden Welsh is really famous is because the mathematics that's behind it, rather than the actual numerical algorithm. And of course, now you can see this jump when there was O of n algorithms.
So, Alan?
Yep.
One of the nice things about Golden Welsh, of course, is that you can adapt it to different ways.
Yeah.
Is that so? I'm not sure which the two dots above it are, but is that true of those other two methods that were competitors at the same time?
So the Golden Welsh algorithm needs a three-term recurrence.
Right.
So you could do this. You could do exactly what I said, with initial guesses being equally spaced, but instead of doing asymptotics, use the three-term recurrence. Then everything I said would also hold in the same generality as Golden Welsh. Right. So there's this slower method that's. So the point is, I don't think the Golden Welsh algorithm is needed. It's never the state of the art, though the mathematics behind it is beautiful. There's always an algorithm out there which can be the state of the art if you give me the three-term recurrence or just the weight, or any other way that you want to characterize a polynomial. There is a method out there which does beat Golden Welsh. Obviously, Golden Welsh you can write in 5 lines of code, and none of the other algorithms you can do that. The algorithm here is like maybe 50 lines of code, which is more. So everyone says, well, there's no point in calculating Gauss quadrature rules to such large n anyway. But I think one of the biggest applications of this is really psychological. It really tells us that Gauss quadrature rules are cheap. A numerical analysis is scared of a large Gauss quadrature rule because they think it's expensive to compute. But when you can compute 1 million of them, it's so cheap. There's no point in tabulating them because you can just compute them on the fly whenever you need. Also, if you need really high precision, like what David Bailey does in experimental mathematics, you can't use a composite quadrature rule. You've got to be global. You can't start piecewising things, otherwise you hurt the convergence rate. So if you want to keep things geometrically converging, you've got to be global. And some people have started using this in astrophysics for doing L2 projection on spheres that they're using for the microwave background. Okay. So right now, what I've explained, it uses asymptotics, but it doesn't use the fact that those asymptotics depend on trigonometric functions at all. I didn't use that here. I was able to use the boundary asymptotic formula that involved Bessel functions perfectly fine. So the second part of this talk will need that fact that the interior asymptotics do involve cosines and sines, trigonometric functions that I understand. So I'm going to concentrate on trying to derive an algorithm to compute this matrix vector product. This matrix vector product is to evaluate Legendre expansions at some nodes. That's all I want to do. Instead of evaluating Chebyshev expansions, which we know how to do because they're just cosines, I want to evaluate Legendre series expansions, which we don't know how to do because they're not just cosines, they're somehow a mix of cosines in the interior and something else at the boundary. So Just as an aside, this slide, I always think of fast transforms as just polynomial evaluation. So the discrete Fourier transform, for instance, you can think of this in terms of signals, but you can also think of this in terms of evaluating a polynomial. Here, this is a description of the discrete Fourier transform. The fast Fourier transform, what it's really doing is just evaluating a polynomial in the monomial basis at roots of unity. There's nothing more to it than that. It's just evaluating a polynomial in the monomial basis at roots of unity. They happen to be a minus sign there, so the roots of unity are just indexed in reverse. That's all the fast Fourier transform really does for you. It's a fast scheme to evaluate that polynomial. Or the discrete cosine transform, all that's really doing is evaluating a cosine series at certain points. Or the discrete Chebyshev transform is just evaluating a fast way to evaluate Chebyshev expansions at different points. All these discrete transforms are just fast evaluation schemes for different polynomials in different bases. So the discrete Legendre transform, this is the one I'm talking about, is just a fast scheme for evaluating these polynomials. Or the discrete Hankel transform, which we can also do, is this thing which is used in image processing. And these types of fast transforms are big business, at least in the US. So nowadays there's Leslie Greengard, who uses very careful numerical approximations to do the fast multipole method, and there's a huge group behind him. There's also people that do butterfly algorithms that are concerned with generalizing the fast Fourier transform in all its different contexts, and there's a huge group behind them. And then there's people in Germany that use a divide and conquer type approach, which is also generalizing the FFT in different ways. This is just lots of people are working on it, and the essential point is fast transforms of some sort of big business. They're very important. And I'm going to derive a fast transform based on asymptotic formulas that rely on the fast Fourier transform, the algorithm that we numerical analysis love because it's extremely efficient. And it's really simple. We actually all know how to do it now. It's take this asymptotic formula and plug in this theta k, which is equally spaced points. Plug in those equally spaced points, and you get this formula for the Legendre polynomial evaluated at those points. If you think about this, for every n and every k, you actually get a matrix decomposition, which you can write like this. And I haven't given you the derivation, how you go from the top line to the bottom line, but let me just talk you through how it looks. Okay. There's a cosine here, which involves lots of things. You can rewrite that using trigonometric identities as cosines times sines, right, as separate all those things out. Every time you see a constant, which just depends on n, that can become a diagonal matrix. So here, this guy becomes a diagonal matrix. Here, when you think about this, for every n and every k in this matrix that I'm trying to evaluate, to do a fast matrix vector product. This Cn here is just the regular discrete cosine transform matrix. It's just got cosines in it, evaluated equally spaced points. And here's the discrete sine transform, which is exactly the same, but involves sine instead of cos. And it's just because the asymptotics involves trigonometric functions. When I write this down for every entry, if I do this to every entry in my matrix, I will get a matrix decomposition just like this. And I can apply this matrix to a vector extremely fast if I forget about this error term. Right? Because this is just a bunch of diagonal matrix, discrete sine transforms, diagonal matrix, discrete sine, cosine, diagonal matrix, and a sum of them. So if I wanted to apply this to a vector, it would be extremely fast. Does that make sense? The only trouble is the error term.
What does extremely fast mean? Is it in n log n?
Yes,
or
n log n. Extremely fast is n log n because discrete sines and discrete cosines transforms can be computed in O of n log n using the fast Fourier transform. And that's because cosines and sines are constant phase, constant amplitude across that whole That's how you get that.
How large is that constant in front of the n log n? At what point does this become profitable?
I will show you. I will show
How
you
large
this.
do these vectors have to be?
I will show you. In 2 slides, I will show you the break-even point between the direct. I still have to worry about one thing, because here I've not kept my rule, which is only use asymptotics when they're valid. Right? I haven't done that. I've just written it down. I haven't told you this. So right now, if you went away and tried to use this matrix decomposition without thinking anymore, you would be like, oh, this algorithm is numerically unstable, because I'm not keeping my rule, which is only use an asymptotic formula when it's valid. And that's because I haven't worried about this error.
By the way, the Rn of theta k, I assume that the statement that this is asymptotic says that that's a little o of something.
Yes, I
What
will
is
give
it
you the.
what is it a little o of?
It's a little o of n to the minus capital M plus a half. So I'll draw it. It's little o of n to the minus capital M. So as n goes to infinity, this goes to 0. This is just it. This is just the boundless error. We don't need to work out that. I haven't done the theta there. There's a boundless error. So let's be careful and let's stay very safe, and let's only use the asymptotic formula where it's valid. If I took 5 terms in that asymptotic formula, I can draw a curve in this matrix. Okay? In this matrix, I want to compute its matrix vector product. On the inside over here, where n is large and theta is in the middle of the domain, this is the area of that matrix that I can use the asymptotic formula numerically stable. As I increase m, you can see I shouldn't use m equals 5, I should at least use m equals 6, because look how much I gain. Right? When m equals 6, I can use the asymptotic formula in this region, but not outside. And when m equals 15, I get this area. For every m, I can draw the error curve, and I know this almost exactly. Here's the error bound, this explicit error bound that was worked out by Stilcher in 1890. He tells us that this bound is almost tight. So I can just draw these curves using this bound for every m. So the game will be only use that matrix decomposition here when this error term is small, only in this region. Well, only in. I don't want to use the asymptotic formula in this region over here. I only want to use it over here where it's safe. So this is how it's just a matrix partition how you do this. You just cut up the matrix. Here's the error curve that you get. Here's the error curve. I'm not allowed to use the asymptotic formula outside of that in this part of the matrix. I'm only allowed to use it over here. Okay? That's my rule, to keep things numerically stable. And now I have a game. I'm not allowed. I can only cut up. I can only partition this area inside here by rectangular matrices. The reason I need to use the discrete cosine and the discrete sine transform, and I can only use those if I apply the thing on square matrices. I can't use them on crazy shaped matrices. I've got to use submatrices. So I have to partition this boundary up with rectangular square or rectangular matrices, just like this. But if I do that, I end up with this grey area where I'm not allowed to use the asymptotics. I'm going to just compute that like directly. So there's this game. You notice I've snuck in this parameter alpha, and that will be very important because I'm going to prove this theorem, at least show you how to sketch the idea, and that is using this idea with these asymptotics. I can evaluate Legendre expansions with this complexity, O of n log n squared over log n. Just some complexity, and just notice it's less than n squared. It's like n log n, really. And then I've stuck in that parameter alpha. So now let me tell you what we can do with the alpha. If we choose the alpha too small, what will happen? We will not use very many matrices to approximate that curve. And what will happen is that grey region will be very large, and there won't be many rectangular matrices like this. So on the scale of things, it will be really expensive to compute that grey area, but it will be extremely cheap when we go to use the asymptotics. If I pick alpha too large, I will partition this curve extremely finely, using lots and lots of different rectangular matrices. Every time I do a new partition, I need to compute new discrete cosine, discrete sine transforms every time I partition. So using the asymptotics, if I refine that curve extremely finely, will become very expensive. But I will have hardly any grey area left, so evaluating the grey area will be really cheap. If I pick alpha just right, I can balance these two costs. If I pick alpha just as 1 over log n, I can balance these two costs and I get an optimal complexity algorithm for this scheme. Now I've got to balance these two things like this. And this happens to be the choice of alpha that balances these two things. So now let's see the crossover between direct versus asymptotics. And in fact, the crossover there's essentially no crossover. The crossover, it basically it keeps with the direct algorithm until n equals 1,000, and then it becomes faster. They got the same accuracy as well, because I've been very careful about using the asymptotics only when the asymptotic formula is very accurate. So essentially, there's a good reason why it matches the direct, and that's because I have this alpha which depends on n. When n is really small, like n is 500, alpha will tell me there will be no partitioning. You should do the direct algorithm everywhere on the matrix. But as n increases, alpha will kick in and tell me I need 1 partition, I need 2 partitions, I need 3 partitions as n grows, and I will get exactly this complexity. This is actually how underneath we were computing the fast convolution of that complicated function. We were evaluating Legendre polynomials of degree 5,000 using this. We were just over here somewhere. Or I could have done a million degree Legendre, evaluated a million degree Legendre expansions using this. And there's a very good reason why we need Legendre. We can't do this with Chebyshev. We've got to use Legendre. Does that make sense? So the point is, these interior asymptotic formulas, knowing exactly when a special function looks like a trigonometric function, gives us a way of deriving direct algorithms based on this. And the point is, the competition has a huge amount of pre-computational cost. They go away and they basically numerically compute how a special function looks like a trig function. Numerically, they go and do this thing numerically before they start. But by sticking in asymptotics that have already been generated and derived, we can just remove all of that pre-computational cost. So this is the timing I get when I open my computer, I turn on my computer and I run it for the first time. This is what I get. I get the direct algorithm. I get that there's a crossover n equals 1,000. If you go to previous work, they will get a similar crossover, but that's after they've run it a few times. They've saved some pre-computational cost. So by allowing us to do this with no pre-computation, we can we have a better way of getting adaptive algorithms. We can now adaptively choose n. We have huge flexibility. So I have this transform in mind that I want to apply this to, and I'm finding it tough. So this is what I'm working on right now, and this is to compute the fast spherical harmonic transform, which is used in weather forecasting. And all it's really doing underneath is just evaluating an expansion at some points. And those expansions involve some special functions that do look trigonometric-like in the interior, but the trouble is the classical analysts haven't worked out the asymptotic formula for them. So somehow I'm going to have to work it out myself, which is a very hard task, actually.
Maxwell didn't do that?
I don't think he did associated Legendre problems, which is what these are. Or the ones that are out there are just like leading term asymptotics. They're not the full whammy that I need with a general M that I can just plug in, right? So somehow I need to derive that myself, which is proving very difficult actually. But the reason that I want to use asymptotics on this is because at the moment in weather forecasting, they do a huge amount of pre-computation before they start the weather forecasting. On this transform, to get this transform to work. So, for instance, here's the red line is this pre-computational cost that you need with the current algorithm, current best state-of-the-art algorithm. And the green line is what would happen if you use the direct algorithm without any fancy stuff. You just evaluate this directly. And the blue line is what happens after you've done that pre-computational red line. You get this complexity in the blue line. So right now you have to do about 100 or 1,000 applications of this one expansion just to make your pre-computational cost worth the effort. It kind of feels a shame that you have to do so many. The pre-computation is so expensive. So I want to remove the pre-computational cost so that this can be applied in an adaptive way in weather forecasting, and eventually derive a new generation of fast algorithms that don't have this pre-computational cost for really adaptive computing. I can choose the degree in my expansions adaptively, and everything is going to work out fine. Thank you.
Have time for a few questions.
So, I like your Gauss Quadrature algorithm. I still I don't feel like you're being entirely fair to Golub Welsh for the following reason. I want to clarify because I think there might be some interesting connections here, which is if you run QR to find the eigenvalues of that tridiagonal matrix, it's order n cubed. It gets expensive very quickly. Right, but it's a nice tridiagonal matrix. So if you run the Grail algorithm of Parlett and Dillon, you're back down to order n time.
Order n squared.
If you just want the eigenvalues for the tridiagonal.
Oh, okay, but you also need the eigenvectors, right? For the weights.
Well, except that you could use that plus your technique for computing the weights, right? So the other thing is if you want the eigenvectors, you can compute individual eigenvectors without computing all of them, and you only need one eigenvector for Golub. So comparing to the order n cubed implementation.
I was comparing to the order n squared.
Okay.
Implementation, which is using the symmetric Jacobi formula.
Okay.
Yeah.
But what I wonder is, going back to the case of alternate weight functions.
Yeah.
What you required is that you understand the asymptotics of how your polynomials evolve. Is there a way to understand that for very general shape functions that would help you with this, or is this something that's?
Yeah, a month ago I wrote a paper with some people in New York and in Sydney that's doing exactly what you're trying to explain, where you only know the wave function. You only know the wave function, you don't know the three-term recurrence, you don't know the asymptotics. And we showed that you can do the same thing. You can actually numerically derive the asymptotics based on the wave function alone. I think that's what.
Yes. That's
So
what
Golub Welsh needs the three-term recurrence, and the GLR algorithm needs the differential equation that this thing satisfies. They all need something. But the point of this paper was to show that you just need the weight if you're thinking about in terms of asymptotics. I don't know if this could generalize to the Golomb Marsh to get the three-term recurrence. It might be. I don't know. I haven't thought about that. That's cool. Yeah. There's this fast, because here we're not concerned with just standard Gauss quadratures, but also more exotic Gauss quadratures where there would be no hope of deriving the asymptotics analytically, but we could derive it numerically, and it was using Riemann-Hilbert.
I mean, the flip side of this, of course, is if you could, there's an awful lot of tridiagonal eigenvalue problems that are essentially coming out of things like this.
Right.
So if this is something that beats the Grail algorithm on that class of problems, that might be worth adding to LAPAC or a similar system.
Well, yeah, I haven't thought about that. Maybe we discuss at some point.
So when we were talking about the amount of pre-computation, this may or may not be a problem given the specific application.
Yes.
In weather forecasting, do they really have to run it those thousands of times after which the blue curve becomes?
Yeah, typically at the moment in their simulation they run it many, many times, often with some random inputs, so they get some Monte Carlo simulations. So they are really in a regime where the pre-computation is not as a concern. That's why they're kind of okay right now with the algorithm they use. But in my world, everything's adaptive. I want to select n so that it approximates a function to machine precision. I want to adaptively choose that n. I'm thinking more like that. And then this pre-computation hurts me because I have to change n. And every time I change n, I have to do this pre-computation. And I don't want to do that. I want to feel connected with the algorithms.
Everything don't do adaptive framework at all.
Well, they can't do it right now with the algorithm they have, because every time they change n, they have to do this pre-computation. Hopefully, well, it would be nice if they could. I assume.
How do you check your error estimates in practice?
I don't check them because they're analytic formulas. I just know that the error is good.
But you have to evaluate them, right? And you have to.
Well, I actually rearrange it and get like a criteria. This entry on the matrix, I can use the asymptotic formula. This one I can't, and I can sort of draw that curve. Right. And I always round things towards so that I'm pessimistic in my rounding. But I don't ever have to evaluate my error or do that with the error curve. Does that make sense? I'm not sure I understood the question. But these two, if you compare the direct algorithm computed in quadruple precision against the fast algorithm, we have a result in our paper which shows there's no error growth. Right, so we've used the asymptotics very carefully, and it's worked.
The Gauss quadrature is for one-dimensional interval. There's a vast literature about two-dimensional interval. Do you have anything to say about that?
Only the fact that if I go back through the way that if you look here, the way that I'm approximating 2D functions is by low rank approximations. Now, if you think, once I've done this approximation, if you're happy with that, then once I want to integrate this function here, I can write that double integral as a sum of 1D integrals, 2 times k of them. And then I can just use standard 1D algorithms. So often we say with this work that we can do 2D computations with 1D algorithms once we've got the low rank approximation. That's
No, but I'm thinking more about the stuff about discrepancy.
right.
Stuff Alex Kantorovich wrote a suppository article
Okay.
in the Bulletin a few years back.
Okay.
It uses all sorts of number theory. It's very interesting.
Yeah, I don't know that work.